last day of this program, and so we'll start with maybe the person that was the more coming the more early in this program, that participated to the full month. And actually, I have to thank everyone. I was very happy to be able to see almost all the people working in this field, the most prominent professors in this field, and it was glad to see all these different kind of people, all these theoreticians, all these experimentalists trying to discuss between themselves, and sometimes trying to agree even between themselves, and sometimes even being able to understand between each other, which is generally not very easy. Okay, so now Professor Ramadurai will talk to us about the neutrino-induced homochirality.
I'm an astrophysicist, as you can see from the address, and so I'm very grateful to Axel and others, organizers, for giving me an opportunity to interact with so many chemists. This is the first time in my life I have come with interacted with so many chemists, and definitely it has given a complete new insight into the way in which the chemists think. So sitting through the lectures of so many chemists, I could see the difference between our way of doing things and then chemists' way of doing things. So what I am going to do today would be to give you a simple presentation of how the weak interactions, which is mediated by neutrinos, can give a unique answer to the homochirality problem. And since most of you are chemists, I thought it would be nice for me to start with some introduction, which may be boring to people who are physicists here, but I thought that it would be interesting for the chemists to know about some of the characteristics of the fundamental forces in nature. For example, the strong interaction in which the nuclear reactions take place, if you take the strength to be about 1 unit, the electromagnetic interaction in the same unit comes to 1 by 137, find such a constant. And the electromagnetic interactions is the one which is of interest to all you chemists, and all the bond energy, everything is calculated by using the electromagnetic interactions. And as you can see, strong interaction, the nuclear reactions are nearly 2 orders of magnitude or 3 orders of magnitude more stronger than this electromagnetic interactions. And almost all the elements with which all you chemists work, they are all synthesized using the nuclear reactions, that is strong interactions, are the things which use. And they are all synthesized during the evolution of stars. So I will go through that also a little bit, because of the fact that what I am interested in is to telling you how the neutrinos are produced from the supernovae and how they are going to affect our homochirality problem. Of course, the premise with which I am starting is that all the biological molecules might have originated in the interstellar medium, and probably their homochiral nature has already been established in the interstellar medium itself. So that is the proviso with which I am starting, and I will slowly go to the other kind of things. And as all of you know, weak interactions essentially the beta decay is something which all of you are familiar with. This particular thing has a strength of around 10 to the power -5 in this kind of arbitrary units. So it is really weak, extremely weak. And the weak interactions are mediated by the intermediate vector boson. They can be charge current weak interactions or neutral current weak interaction. Let me not bore you with all those kind of details. But what I want to tell you is the following. The electromagnetic interaction is now unified with weak interaction by Abdus Salam, Weinberg and Glashow, and they have shown very clearly there is nothing called, there is a electromagnetic interaction is only a part of the electroweak interaction, in which weak interaction has been separated out earlier. But why we are bothered about weak interactions? Weak interactions are the basic building block of the stars. I tell you why. The first interaction through which the sun gets its energy, the fusion reaction, proton plus proton goes into a neutron plus a positron plus a neutrino. This is the first weak interaction. That's the reason why this is the slowest of the reactions, and you may be surprised that the number of neutrinos produced per second in the sun is around 10 to the power of 37. Actually, if you find out, if you see the flux of neutrinos coming from the sun, for all of us are being exposed to the flux of around 10 to the power of 10 to the power of 13 neutrinos per second, solar neutrinos. So this is something which is, but it doesn't do anything to us because of precisely the reason is the weak interaction. The interaction is so weak, so it is not doing anything to us. So immediately you will wonder, then why you are talking for homochirality, which is extremely difficult, even with the chemical kind of various processes which you are talking about, how you are going to bring this about. So I will slowly come to that. The first thing which you have to remember is how the stars are formed. The stars are formed by subgravitation. Can it form by just subgravitation? So essentially, if you want to form the stars, star means when you call an object a star, when it starts nuclear reactions. The nuclear reactions means you need to have a temperature of at least around million degrees, a few million degrees. So a few million degrees if you want to have at the center to start the nuclear reactions, then if you want to have just pure self-gravity, then the required mass is around 2000 solar masses. So you cannot just form one solar mass star and then under self-gravity it cannot come. Then how can such stars be formed? After all, we know that lots and lots of slow mass stars are there. How these stars are formed? These stars are formed, then essentially there should be some impulse which is given by some particular event, and this impulse can be given by a supernova explosion. When the shock waves from a supernova explosion impinge on the general interstellar cloud, then this is going to give you the additional force which is necessary for the gravity to operate to get the minimum temperature to around a few million degrees, which nuclear reactions can take place. So it looks as though that a supernova explosion really aids the formation of stars. Of course, you can ask me, do you have any evidence for this, or is it only one of those astrophysical speculations? It is not. We have evidence from the meteorites, the primitive meteorites, carbonaceous contains of type 1, that when the solar system was formed, there was live aluminum-26 present at the time, and the formation of the solar system. As you know, aluminum-26 has a half-life of very 500,000 years. So, the solar system should have been formed within 100,000 years of the formation of the synthesis of aluminum-26. Aluminum-26 is very easily synthesized in the carbon burning envelope of the supernova, and so this is another evidence in favor of a supernova-induced star formation. And actually, this is not only aluminum-26 one of the evidences which I have given, but there are other anomalies which also give the same kind of sodium-22 has been seen live and things like that. So many things are there, that kind of things. So it looks as though that supernova has something to do with the formation of solar system. So if the supernova is a thing which is helping the formation of the solar system, first of all, we should like to know how exactly a supernova explodes. Then only we can say that this particular thing helps in formation of solar system, and this requires a small digression of how the stars evolve. As you know, the chemical energy is not sufficient to, for the stars to shine, because it is too inefficient. It is the efficiency is less than 0.01%. So chemical energy is not responsible for the star. The stars, as you, all of you by now would have known, it is the nuclear energy which is responsible for the stellar energy. So, for example, a star like the Sun, which is a low mass star, it shines with hydrogen fusion. Hydrogen going to 4 hydrogen atoms fusing to become helium-4, and this fusion energy is what we are. We are getting light from the sun. We are getting the energy from the sun using this. But how long this can last? So, after all these things takes there are only finite amount of hydrogen available. After all, so and the temperature, central temperature is around 6 million degrees. So with 6 million degrees, you can have the hydrogen burning going on in sun for probably around 5 billion years more. So around 10 billion years, around 9 actually to be exact, it is 8.98 billion years, that kind of thing, but for the hydrogen burning taking place. Okay, when the hydrogen is exhausted, what happens? When the hydrogen is exhausted, naturally there is nothing to support resist the gravity. So gravity takes over and it starts contracting. When it starts contracting, the temperature increases, and the temperature increases to such an extent so that you can have the burning of 3 helium atoms joined to 3 helium nuclei fused together to become carbon-12. That is a helium burning reaction, but this requires a temperature of more than 10 million degrees. So naturally the star has to contract. So what happens is the following: when the star contracts, the temperature increases. When the temperature increases, then you are having the pressure increase cause the gravity, and then so that again you reach another equilibrium configuration kind of thing. So this is the case with a solar mass star. So what happens is the following. Essentially, the binding energy is what is used as for the supply of energy for what we call it fusion energy, the energy for the support of the star. And what happens in the case of stars or low mass is, that is stars which are of around 2 solar masses. Actually, this particular thing, I think it would be nice to give the reference. This Kippenhorn and Weigert, this stellar physics. There are 3 volumes. This is in volume 2. Then what happens is the following. The pressure directly is increasing. Once the temperature is increases, you know that pressure increases. But you reach a situation in which the electrons are there. These electrons, when, for example, when the temperature becomes 10 to the power of 7 degrees, helium burning takes place. So you have the carbon 12 forms. And then when the helium gets exhausted, then at that time what happens is the following. We have a lot of electrons. These electrons are slowly rise to the higher levels and they become degenerate. What do you mean by degenerate? That is, we have all the levels, the energy levels are occupied by the electrons. And then if this is the case, what happens is the pressure, you cannot compress the thing still further because the degenerate pressure, the degeneracy, electron resists being pushed from one particular energy level to lower energy level. It is not possible because already it is all occupied. So this is what is the new pressure, which is called the degenerate pressure, which is being given by that. This was discovered by Peter Fowler in England in 1920s. And then this degeneracy pressure is able to halt the thing. But there is one snag in this. What happens is when the degeneracy pressure is nothing to do with the temperature increases, that is, for example, in the ordinary gas pressure, it gets to directly proportional to temperature. Here, when the degeneracy pressure is there, it's only the pressure, the degenerate pressure is not connected with the temperature at all. And then, when the nuclear reactions take place, when they release the energy, then the temperature of the material increases. And as you know, the nuclear reactions are extremely sensitive to the temperature. It is T to the power of, for example, helium burning to T to the power of 27. So 27 the power of these things. So what happens is the following, that when you are having a stars of mass around 5 to 7 solar mass, after the carbon 12 burning before that takes place, you find the whole electrons have become degenerate, and the carbon 12 burning, when the carbon burning starts, it is really explosive, and then the entire star gets disrupted because the energy is increasing, but that is not increasing the pressure. Pressure is the same thing. So, and the energy, the sudden explosive increase of energy is something which disrupts the entire star. And this is one type of a supernova explosion. In this explosion, what you are getting is, how does the energy is carried to the outer envelope is by the neutrinos. So these neutrinos carry the energy to the envelope, and then you are having the explosion of the star. This is what is called a supernova. When I was telling you about supernova explosion, this is what happens. This is one way. There is another way. For example, if the temperature is such that it is not degenerate the electrons do not become degenerate, then gas pressure is there. This happens for higher mass stars. So massive stars go through the hydrogen burning, helium burning, carbon burning, oxygen burning, silicon burning, and it reaches almost the core becomes completely iron. As all the chemists, all of you know, iron is the most tightly bound nucleus. So by fusing iron, you are not going to get any energy. So now we have reached an impasse. Now what happens is we have reached the iron catastrophe. So now what happens is the iron, then the gravity, the core contracts, the iron, the energy supplied by the temperature goes to dissociate iron into 14 helium-4. The helium-4 again dissociates, and then you get completely then lot of neutrinos are released, and the sudden kind of thing, neutralization of the core leads to the explosion of the star. This is what is called a type 2 supernova explosion, in which lot of neutrinos are released. So, in any case, all these stellar explosions, they release neutrinos. And you can model from the neutron star mass of around, let us say, 1 solar mass, neutron core is formed. You can find out how much is the total number of neutrinos which are emitted in this. And the number of neutrinos which are emitted is around 10 to the power of 57 neutrinos are emitted. Per supernova explosion. So it is 20 orders of magnitude more than what you get from the sun, kind of thing. So I agree that we have the problem of weak interactions. So the weak interactions is not going to change the structure of the, for example, the other day when I was presenting in the informal thing, Raphael was telling me about the difficulty of changing the structure of the thing from the D to L by this kind of weak interactions, how difficult it is. And then it is almost impossible, and then actually Rao was telling me, Maya was telling about the difficulty about these things. And then when we talked about the thing, that's a real education for me, because from thermodynamic arguments, we find that the energy, the parity variation energy, it is much smaller. So then this is the most stable structure. So I would say that it goes to D, it goes to L, whatever it is. But he said, what is the kinetics? What is the kind of process by which this takes place? So this is what he was asking. So I have this particular, some kind of an indirect answer to this today, and that's what I'm going to present now. See, what happens is the following. And I said electroweak interactions. As all of you know, there is a spin orbit coupling. Formerly, we were thinking in terms of only electromagnetic interactions. But there is a weak component, weak charge associated with it. So we have to take into account the coupling between the electron and the nucleus due to the weak interaction also. It's not just only electromagnetic interaction, there are weak interactions too, additional we have. Essentially the weak interactions are the parity-violating interactions. As you know, this is all the other forces are all achiral. Only weak interactions is the chiral force. We have the left-handed neutrinos and right-handed antineutrinos. This is the kind of problems which we have, like left-handed electrons and right-handed positrons. Essentially what we mean by is the spin and the momentum vector when they are anti-parallel, then this becomes the electrons or left-handed particle. This one left-handed. In the case of positrons, spin and momentum vector are in the same direction. Then this is the case of positron, this is the right-handed. As chemists, you know that this naturally has its own effect in the handedness of the molecular physics. This has its own effect. And what is very important in this particular thing is we have to compute spin orbit coupling. In addition to that, we have the parity violation coupling is also there. So when you compute the energy of this, we have to really take into account actually this is reference to this is so the parity violation energy EPV is nothing other than the expectation value of the parity violation operator on the wave function, electron wave functions, and HP is nothing other than the Fermi coupling constant Q by 2 root 2 sigma I m Q W n. This is the gamma matrices. The rho n at or n. This is the electron position. I am going to write only a few equations, don't bother too much about it. I am just giving you the result, but I thought that I will tell you what exactly is the kind of things involved in this. The Fermi coupling constant in the units here, what we are going to do, don't come confuse it with the thing. This is around 10 to the power minus 14 atomic unit. And gamma phi, the gamma matrices, the spin matrices, also, all of you know that kind of the Dirac spin matrices, that is precisely what it is. And this is the normalized nuclear density rho n, and Ri is the position vector of the electrons. So essentially it is the electron and the nucleus, there is an interaction. That's precisely what is happening. This interaction, in addition to spin orbit interaction, we have the parity violating interaction due to the weak interaction. That's precisely what we are talking about. So this HP is the operator which takes into account the parity violating part of the thing. And actually, if you want to do a proper relativistic approach, can also be done. But to understand easily, I would give you a non-relativistic expression of this. H spin orbit coupling is given by, this is Bohr magneton by H cross sigma. Z is the charge of the nucleus, then Ri minus Rn. These are the position vector of electron and nucleus. Minus 3. This is the sigma I told you sigma matrices, which takes the spin orbit. This is the spin orbit part of it. Into Ri minus Rn into Pi. Where Pi is the momentum of the electron. And HPV is minus GF by 2 root 2. Now it's 2 times we have to put 4 root 2. MEC sigma of QWN, which is Pi dot sigma I dot delta Ri minus. This delta takes into account, this is equal to 1 when it is Ri equal to Rn, otherwise it is 0. That is, essentially we are taking the most dominant component of this parity reaction here. And I think the sum and substance are these. I will give you the final answer for the EPV. Is minus 2 by H cross sigma J not equal to A. Real part of expectation under A to HP J into J H spin orbit divided by omega. So this is how the parity violating energy is calculated, and why we are talking interested in parity violating energy.
Well, what is A and G?
Yeah, okay.
A is somehow ground.
This is two states, A and J. Initial state and final state.
What kind of state is it?
Yeah.
What kind of state?
This is the state of the electron in the final, before the interaction, after the parity violating interaction. That is the state.
In the atom or molecule, there are atomic or molecular states. What do you think?
Yeah. And one thing which you have to remember here is, when you are talking about spin orbit coupling in these things, it is very, as chemists you know that molecular orbitals configuration is very important. Conformation of molecular orbitals are very important. So the wave functions properly you have to put in, taking into account the conformation of the molecular thing. And then this particular thing is responsible for, if you go to I already put a charge in this particular thing. This particular thing can be proportional to z to the power of 5 is the the charge to the component. As you go to higher and higher elements where higher charges are there, then this increases, the spin orbit thing, as well as the energy increases, which is what we expect anyway. So that's what it is.
So it goes as z to the 5 because the parity violating term goes as z,
yeah.
and the spin orbit coupling goes as z to the 4.
Yeah, that's it. That's it. Okay. So with all this, what we have found out was the parity violating energy for so the higher the element, then the more will be the parity violating energy, and this parity violating energy is the order of some 10 to the power minus 18 Hartley into 10 to the power around 10 to around 100 into minus 18 Hartley for the R type nitrogen bromide, and then this is 139. This is for right bismuth. So we really have extremely small, around 10 to the power minus 17 thing which you are talking about, where we see the asymmetry factor.
It's only to ask what is there is an initial state and an final state in the interaction with it. What type of change is in the molecule? There is a change of electronic configuration.
Yeah, the change of
electron expulsion.
Yeah, essentially it is not essentially what happens is, because of this parity violation, the initial state is in, let us say, in a D configuration. The final state becomes the L configuration.
I agree, but what type of electronic change can occur with the interaction with the neutrino?
I don't know. I don't understand what type of change is.
Because the energy, what type of energy is in the change of the
It's
electronic
not got into
configuration?
the neutrinos yet. This is just the parity violation.
Parity violation. I am not talking about neutrinos here at all.
Of atomical and molecular
Yes, of course,
energy
of course.
states. So A is the ground state
Yes.
of the atom.
And A is the excited
But
state.
there is no interaction with the
And
neutrino.
it's staying in the ground state, but
Yes, of course.
but those J's are all the
Higher excited states.
And this is standard time
Yeah.
independent perturbation.
Yeah.
theory.
Yes, yes,
You're
yes,
mixing
yes.
the
Yeah.
excited states into the ground state
Yeah, yeah.
via these two interactions, HPV and HSO. And it's a static situation.
Yes, of course, but what is the type of interaction between a neutrino? on
Well,
the
he hasn't
electron?
got to
Now I am coming to the neutrino act.
Yes.
I am coming to the neutrino act. So what happens is the following. So the parity violation reaction leads to an asymmetry of the order of around 10 to the power minus 17, let us say. This is the asymmetry factor which we get, around 10 to the power minus 17. And if you want to have this particular thing, the asymmetry, to be increased to 1, which is we want a completely homochiral thing, essentially this is the asymmetry 1 by A square is the number of interactions which you require. So essentially you require around 10 to the power of 34 interactions, which is really huge. And that is the standards. But we have, I already told you, in a situation like what exists in the supernova, I already gave you evidence that I am not talking about a hypothetical thing. Supernova induced star formation is something which is very likely, as evidence from this live aluminum 27, the magnesium anomaly in meteorites. So from meteoritic anomalies, we know that supernova-induced star formation is a strong possibility. So since the supernova, and we know a supernova emits 10 to the power of 57 neutrinos. these 10 to the power of 57 neutrinos, the original cloud in which you are having, for example, interstellar dense molecular clouds are there, from which the stars are formed, as all of you know. So, in those dense molecular clouds, what we are interested in is the organic molecules. What is the organic molecule component in this particular thing? And this is actually suppose you take a molecular cloud extending to around 10 to the power of 3 into 10 to the power of 18 centimeters. This is actually 1 parsec in astronomical terms. So there is a molecular cloud. Normally molecular clouds are of this kind of extent, and the density in these molecular clouds are around 10 to the power of 4 molecules per centimeter cube. Out of which organic molecules will be around 10 to the power of 1. Around 10 molecules, organic molecules. So, now we can straight away see, suppose that cloud is about a 1 parsec, within a parsec from the neutrinos, from the emitted supernova explosion. Then we can calculate how much is the total number of interactions. This is 10 to the power of 57 neutrinos are there, and 10 to the power of 4 per molecules per thing, plus into 10 to the power minus 3 is 10. And we have the cross section, weak interaction cross section is so low, it is around 10 to the power minus 42 centimeters square. 10 to the power minus 42. Whereas normal nuclear reaction cross sections are the order of 10 to the power minus 29, 20 to the power minus 28, things like that. Whereas here this really weak interaction cross section is so low. And what we have is, this is per centimeter cube, so this is something which we have to, this one by r square into, that is r is 1 parsec, into r cube, that is essentially r, which is 1 parsec, is around 10 to the power of 19. So this comes to around the number of interactions is about 10 to the power of 35. So what happens is,
what was 10 to the 19? What was it?
What is it?
What was this 10 to the 19 factor?
This is 10 to the power of 4 molecules into 1 parsec cubed divided by r square. So this is 1 parsec, I mean this is essentially 3 parsec essentially.
Mm-hmm.
I'm sorry, what is 10 to the minus 42? I missed, what is 10 to the minus 42?
Cross section, yeah?
10 to the minus 42 centimeter square is the interaction cross section. Of the weak interaction cross section. The neutrino interacting, the cross section, neutrino interacting with the proton, neutrino-proton interaction cross section, neutrino-proton and neutrino-neutron cross section is that. And what is the reaction which you are talking about here? The nu plus P going to N plus E plus, this is the reaction which you are talking about. So, already I told you, we wanted around 10 to the power 37 things, we have come very close to them particularly. And what happens is, our sun goes through the several molecular clouds. Once in 200, our sun goes through goes around the galactic center around 250 million years. Is the period of revolution of the sun around the solar system in our galaxy. And this time it encounters several magnetic clouds, several molecular clouds. And these molecular clouds are, and we know the frequency of the supernova explosion is once in 30 years. So the amount of neutrinos which are available in these things is picked up. And so the kind of the possibility of so many interactions are there. So we are having almost the homochiral structure established in the interstellar space itself.
But that's a neutrino interacting with a proton.
Yeah.
How does that get translated into?
This is the neutrino interaction with the nucleus of the molecular cloud. There are the molecules has protons and neutrons and things like that.
How does that get translated into the electronic structure of the atom or molecule?
No, this is because of the parity violation interaction. This is the reaction which is because of the parity violation interaction, which takes into account this particular thing. When a parity violation interaction is there, then the thing goes to the other excited state in which the thing goes. That's precisely the kind of argument is that.
The neutrinos always have the same handedness too, so if there is any kind of molecular influence, it's always going to be the same direction.
So, I have presented a case of the possibility of having a homochiral structure, molecules, in the interstellar space itself. But of course you can ask me that after all these particular things are in the interstellar space, and then then the solar system formed 4.6 billion years ago. So all this particular thing has been transported, but the life as we know it started only around 3.9 billion years or something like that, 3.6, 3.9 billion years. In this particular interval, isn't it possible for the molecules or all these structures to be racemized? There is a strong possibility of racemization in the Earth, in the particular thing, but the racemization is not going to be complete. So it is going to be actually, now we are starting with really homochiral, and then we are going to the racemization over perhaps 800 million years will be of the order of perhaps around 20%. So we already are having, we don't know the kind of numbers for those things because this is something which is Bonner has been talking about. There is a racemization is possible and things like that. But the hardcore numbers are not available, at least as far as I am not aware of any of those numbers. So I am trying to tell you is the following, that unlike what yesterday we heard, our life originated perhaps in a interstellar molecular cloud from which our sun formed. Even before, perhaps our life is coeval with the formation of the solar system. It is not necessary for the life to wait for the sun, the earth to form, and then we form all these compounds and things like that. All these things can take place. The conditions are there, right, even in the interstellar medium. And we don't have to wait for the origin of life for the earth to be formed. I think I will stop here.
Okay, so for the questions, yes,
But you're talking about the origin of homochirality, which is only the very first step. You're saying that can happen before considering planetary formation and whatnot, not life itself. But I'm still not clear how weak interaction from the neutrinos, this vast flux of neutrinos smashing into atoms and molecules into into dust clouds. How that translates into homochirality? Are you saying there's a preferential destruction of one enantiomer over the other because of the
precisely
handedness of
Yeah.
the neutrinos have the one-handedness?
Yeah.
So they're
Neutrino, you see, these particularly emits
preferentially-
positrons destroy.
Right. But there's no actual evidence for this. No one's ever seen neutrinos smashing up atoms or molecules. Okay.
Yeah, I agree. Well, for example, I wanted to find out whether is it possible to experimentally demonstrate whether the neutrinos whether doing that. So I found that even if I take 1 kilo of camphor and then expose it to neutrinos from the reactor of the order for nearly 1 year completely, I expose it. Let us say that even then the amount of the change is going to be 10 to the power of minus 10, which is extremely low, and that's the reason why it is not possible to demonstrate experimentally and in the Earth. This is possible here only because of the fact that we have got a huge mass of the organic mass of the order of around 100 solar masses are available. That is the reason why it is possible. Otherwise, it is not possible to do it and in the normal kind of circumstances.
Another question.
Yeah.
I mean, you're saying that there's this background of 10 to the 37 neutrinos per second coming out of the sun. And
Yeah.
all other stuff. They're not interacting with anything.
Yeah.
Where are they going? Is there some reservoir on the edge, at the edge of the universe? Or, I mean, when one
Just passing through, that's it.
naive
No,
popular description of general relativity, the universe is a bubble. If you send a light beam off in a certain direction, it will come back around and hit you in the back of the head. And the neutrinos sort of just circling round and round the bubble of the universe.
there is actually there's a calculation of the amount of neutrinos coming from right from the Big Bang itself.
Yeah.
There is going circulating, and that particular flux is 2 orders of magnitude more than the solar neutrino flux. So it is not that it is going away anywhere. For cosmological neutrinos, that is nearly 10 billion years, the neutrinos are still circulating.
So we're drowning in them all around us with neutrinos.
Yes.
We are in the crowd of neutrinos there, and
It's not clouds. I mean, the point is, all of us, as I said, for every minute, around 10 to the power of 10 neutrinos pass through our system.
Okay, and that's not just from our sun. That's
It's from all over the cosmology. Yeah.
But it's one thing for neutrinos to interact with matter, and it's another for them to distinguish between chemical enantiomers. I don't.
No, precisely because of parity variation. See, because of the parity variation, it is able to distinguish between the handedness. Because of the parity variating interaction, you are getting the parity variation energy shift to be around 10 to the power minus 17. It is so small, I agree, but there is a small.
Yeah, but the point is, you need a certain mechanism, right?
Yeah.
Like that.
For example, for example, Salam has been talking about this particular thing, as you yourself were saying. There's a tunneling between, I agree it is a small energy difference, but it can strong. What is wrong in tunneling effect taking place? DTL.
Tunneling effect, as you pointed out, you need a small molecule like ammonia, you can do tunneling.
Yeah.
But if you take a large molecule, there is no possibility of tunneling. Like in the Salam experiment of methionine, that you would like to take one and to go to the other. This really has to overcome huge energies in order to do it. So in order to be able to discuss this problem in general, you need a certain mechanism. Somehow a neutrino which interacts with the material, let's say you take somehow how it can induce the formation of the other one. Because if you take small molecules, they are not chiral. You take ammonia, it's not chiral or something like that, these are molecules. The question is, can you have a more realistic model?
I think that probably if it can tunnel, it's not keyword. And if it can tunnel, well, that way.
I was only 2 persons that decided that it's deterministic, you and me. I agree that this is, but the problem here is that you imagine molecular flows of compounds. these compounds must have a structure, must be a racemic clone. It means that must be in the clone must be already the two enantiomer.
Yeah.
And then there is already a small difference between the neutrino interaction in one enantiomer and the other one, and then in cascade in successive symmetry breakings there is the amplification, and here it is the attractive point.
Yeah.
But the question is, what molecules could be in the molecular cloud to be able to give an enantiomeric excess? But that is only corresponds to
Actually, this is what Raphael was also saying. I understand that.
That could give the two enantiomers. It must be a racemic cloud. And
Right.
here is the problem. And
So I understand the thing, and I agree it's a problem, because this is something, essentially what we are interested in, precisely the problem which is the kinetic thing which you are, which we have to say.
in the geometrical structure of the organic compound, because he must have a geometrical structure, a molecular structure, able to have the two enantiomers, and that is normally not found in law.
But interstellar dust grains are
Yeah.
covered in organic crud. It's getting processed all the time. You have an organic
They
complex.
are not
Organic.
compounds given enantiomers. They are not compounds given enantiomers.
Some of these compounds are sufficiently complex. They'll be chiral and they'll be racemic.
What type of compounds are detected that can be chiral in molecular clouds and in planetary systems?
No, they have detected large molecules.
Must have
See,
already the amino acid.
I agree with you, we have detected up to, even amino acid detection is something which people are doubting it, but up to that has been done.
Now look, I am convinced that this the neutrinos is at play, but the question remains that is to think, we could think about polyaromatic compounds giving polymeric structures and so on, and there is then in the polymeric structures it is not necessary to have the two enantiomers. It could be already chiral in this induction, but it must think in molecular structure.
Essentially you are, I understand your question, you are asking for the,
Able to be chiral.
Yeah.
Because
asking the question that what is the thing, molecular composition of molecular clouds in which these particular structure, what is the structure of these particular
able to
molecules?
give enantiomer.
Yeah, but that's something which people have not, of course we have not detected any large molecules other than the maximum molecule which we have seen is around this one. So it's not
we have
possible.
structure, there are no small molecules, but polymeric structure of polyaromatics is something else, because in other case, you need clouds already of alanine or...
Okay.
And that is still not...
But anyway, none of those compounds have been detected in the thing, except that we have the evidence from meteorite that proteins have been seen, the alanine has been seen in the
but not in molecular clouds.
not in molecular clouds at all. Other question? Okay, so thank you. Thank you.